Good evening, everyone. Thank you for joining us today. We know that some of you have started school, so we appreciate that you've made the time to come and join us this evening, despite your busy schedule. And it's your passion for learning about AI that really keeps us at the UT AI Lab going. So last week, MIT professor Sung Han talked about efficient machine learning. And today, Professor Stone will talk about intelligent agents, such as robot soccer players and autonomous vehicles. We also have several talks coming up soon. And so for one, Dr. Qixing Huang will talk about AI and graphics, especially how they can play a role in fields like archaeology, dentistry, and more. And on October 1st, we'll have Fiona McAvoy, an AI ethics writer, researcher, and thought leader based in San Francisco, California, to talk about AI and ethics. And finally, on the 18th, we'll have Dr. Mark Esposito talk about AI and its impact on the business world and the job market. So today's talk is co-hosted by the UT AI Lab and the Open Code Foundation. The Open Code Foundation is an award-winning nonprofit that aims to provide students from low-income families the education and resources required to pursue a career in CS. During this pandemic, they're working to provide internet access and computers to disadvantaged students around the world. If you want to learn more about the mission, please visit www.theopencode.org. Before I introduce Professor Stone, I'd like to briefly go over the logistics of this talk. There will be some audience interaction, but due to today's turnout and some of our audience being on the YouTube live stream, we'll be doing the Q&A through a platform called Slido. You can either go to the URL I've just provided in the chat, or you can go to Slido and enter the event code 82241. And feel free to submit questions throughout the course of the talk. So now I'm honored to introduce today's speaker. Dr. Stone is a top expert in machine learning, multi-agent systems, and robotics. He's the founder and director of the Learning Agents Research Group at UT Austin, as well as the Associate Department Chair, the Chair of Texas Robotics, and the President of the International RoboCup Federation. He was a co-founder of Cogitai and is now the Executive Director of Sony AI America. Dr. Stone is also the founder and leader of the 11-time world champion UT Austin Villa Robocup teams and a co-founder of the 4-time world champion CMUnited robot soccer team. Professor Stone is a distinguished teaching professor, and you'll find his talk fun and exciting. On a personal note, when I was 10, I watched Professor Stone's soccer team play when I visited UT, and that's something that really sparked my interest in tech. I'm very honored to have him today. Now I'll turn it over to you, Professor Stone.
Great. Thank you, Jeffrey. And thank you, everybody, for being here. It's a pleasure and an honor. Let me just share my screen here. And okay. Nope, it's not going away. Let me try that again. Okay, hopefully you can see my screen now. Good. So, welcome everybody. I'm going to talk today about artificial intelligence research and really my path to where I am now, and also to hope to inspire you. And it's going to be at times a little bit interactive, but I really am looking forward to the questions and the conversation that we can have at the end. So, in my view, there are really 3 big scientific questions of our time right now. There's how did the universe originate? There's how did life on Earth originate? And there's what is the nature of intelligence? And it's this third question, what is the nature of intelligence, that really grabbed my attention when I was myself in high school. And I've been in trying to contribute in my own way, in my own small way, in conjunction with many people around the world, to try to understand this really grand question. And I was when I was a high school student, I was very mostly interested in mathematics. I spent a lot of time in math, and really liked my calculus classes and my and problem solving and combinatorics. But I also was getting into computers and computer science a little bit, and started programming, sort of the relatively early days of computers, although they've been around for a few decades. So maybe about halfway from the beginning of computers to where we are now. And in so doing, it sort of, I became just enamored with this question of what is the nature of intelligence. And the path there, I sort of, in my high school, at sort of end of high school and the beginning of college, I started asking, how can we get at this question? How can we understand what is the nature of intelligence? And there's a number of different ways. There are a number of different approaches to trying to study intelligence. One is just to think about it, to try to think, what does intelligence mean? What would it mean for an animal or a person or an entity or a computer to be smart, to be intelligent? And in some ways, this is what philosophers do, and they think about how to encode logic and reasoning, and try to answer the question: is a dog intelligent? Is a person intelligent? What does it mean to be intelligent? Another way is to study human or other animal behavior. We know that where we think of humans as the example of intelligence, and so we could study what people do and try to understand intelligence from that perspective. And that's what psychologists do. Another approach is to study human or animal brains, right? We have an example of a physical entity that exhibits intelligence, and this is what neuroscientists do. But the fourth approach, and I actually sort of thought about all of these. I went to neuroscience classes when I was an undergraduate. I went to psychology classes. But the approach that really grabbed me was trying to build and analyze intelligent artifacts. This is sort of a cross between a computer science approach and sort of theorizing about what can a computer do and what can you make something to do to exhibit intelligence, and also somewhat of an engineering approach. How can we build something that would be intelligent? And so, I think there's merit in all of these different approaches, and there may be other ways to get at the nature of intelligence. But this one, the computer science perspective, is what really grabbed me. So one of the goals of AI and robotics, and I sort of lump these together. I take a somewhat robotics approach to AI, but it's to create fully autonomous agents in the real world. So it could be robots, it could be a self-driving car, for instance. There's a lot of that in the news. Something that can sense, decide, and act on its own in the real world. Or it could be a software program or some kind of a software entity. It doesn't have to be a robot. But the question then is how should we do this? And this is this question of how do we build intelligent artifacts? It's been around since the beginning of the field of computer science. The first computers were invented in the 1940s and 50s, and the field of AI, the term artificial intelligence, was coined in the 1950s. And these the two fields have often really gone hand in hand. At first, there was really only one possible approach to this question of how do we build intelligent agents, and it was to sort of break the problem down into subcomponents. And I'll sort of use a metaphor to illustrate this in a second, and to try to work on the types of the different aspects of intelligence. And so a colleague, Stuart Russell, in 1995 in a talk said theoreticians can produce the AI equivalent of bricks, beams, and mortar, with which AI architects can build the equivalent of cathedrals. And so at the early days of the field, we really needed to be figuring out what are the bricks and the beams and the mortar of intelligent agents. What are the components you need if you're going to build build something that's intelligent. And then we want to have to, then there's the challenge that comes after of how do you put them together. So I'm going to build on this metaphor in the next few minutes. Another colleague, Daphne Kohler, in 2001 said, in AI, we have the tendency to divide a problem into well-defined pieces and make progress on each one. And that part of our solution to the AI problem must involve building bridges between these pieces. So these are sort of two different metaphors, the architecture metaphor and sort of another architecture one of bridges between these different pieces. And so if we do think of the AI being the cathedral that we're trying to build, then what are the bricks? What are the components? And so that's where the field started back in the, again, like 1950s, and for the first several decades, sort of broke into subgroups or sub-teams, thinking about how can we do computer vision? How can we do machine learning? How can we do robotics, manipulation? How can we do natural language processing? How can we represent knowledge and do planning? And so and from each of those bricks, people sort of, the lines I have coming out of these bricks, this is sort of, the research of developments of how can we make better learning algorithms and better robotics algorithms, and sort of making progress, building on each other. And then, the beams and the mortars in the metaphor that I introduced sort of try to connect these. But there's a question here of is this the only way to try to proceed? At the beginning, there really is no option. You have to start with these different components and put them together. But does it get you there? Does it get to the cathedral, or does it get to some other architectural entity that maybe you didn't plan for in the first place? So in this talk, I'm going to emphasize a little bit of a different approach. I would say a complementary approach. I don't want to say that there's any, that it's the only way. That I think that there's actually, I'll say in a minute, that they can be unified. But another way would be, instead of breaking the cathedral into those subcomponents, you could imagine trying to start by building more and more complex, complete architectural structures that include all of the bricks and the mortars and the beams and the connections between them. And so this is more of a top-down approach. It means, sort of thinking about, well, if I want to build this structure, and think of this as an AI application, right? It could be a chess playing program rather than a house. It could be a Jeopardy playing program, or a autonomous car. To build that application, what do I need? What components do I need? And how do I motivate that research and that development to try to enable this construction? And so really, like I say, it's not one or the other. We can try to meet in the middle. And my research over the past more than quarter century now, almost 3 decades, has been trying to sort of take this complementary view of both pushing forward some of the basic fundamental algorithms that are the bricks and mortars of AI, and also focusing on specific applications and trying to use that to motivate the research. And I'll show some concrete examples of that as we go forwards. So coming back to this question of how do we build robust, fully autonomous agents in the real world, one way to do it, the complementary way, is to build complete agents to perform increasingly complex tasks. And what do I mean by a complete agent? I mean a computer program that consists of a closed loop, that can sense the environment, that can decide what to do, and can actually take actions in the environment in such a way that it changes what the next sensations are going to be. And the idea, as illustrated in the previous metaphor, was with the cathedrals and the bricks and the mortars, that this will drive research on the component algorithms and theory. And in my research, and what I'm going to emphasize in this talk, is 2 particular aspects: creating autonomous agents that can improve from experience, which is the subfield of machine learning, and also creating autonomous agents that can interact with others. If you build an autonomous car, you're not going to be the only one with an autonomous car. Your neighbor's going to have one. They're going to need to both pull out of the driveways at the same time and interact with one another on the street. And so that's what we call the sub area of multi-agent systems. And so the idea here is that if we carefully pick the problems, and I'm not going to tell you what problem to pick. I'm going to tell you the problems that I have picked. But really, if you decide to get into artificial intelligence, it'll be your job to decide what are the problems that you find most motivating. And if you do that wisely, it will lead to the good scientific advances. Then that's sort of the mantra of this kind of approach, that good problems produce good science. So what's my research problem? As I say, I've been working on AI for more than a quarter century. And in almost all the talks I've given, starting from my time as a PhD student, I've included this question that's really driven everything that I've done. And it's led to sort of different sort of subtopics and diversions, but everything comes back to this question of how can we make autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And I hope if not all of those words make total sense to you, I hope they will by the end of this talk. So the research areas, this is very much an artificial intelligence question. There are sort of subcomponents of AI, as I've talked about before. There is an area known as autonomous agents. There is an area known as multi-agent systems. There's their own conferences and communities in these areas. Of course, there's a robotics community as well that includes people in AI, but also people in other fields that work on the physical motors and gears and electronics, mechanical engineers and electrical engineers. And this question, of course, also is, as bolded in the agents learn, it's also very central to the area of machine learning. And in particular, I'm going to try to give you some insight today into a particular type of machine learning known as reinforcement learning. And I'm going to do that through an activity that's going to be a little bit interactive coming up. But so this is my research problem in words. The examples of problems, the sort of the structures that I've built towards more concretely are the ones pictured here, and I'll show you some videos. I'm going to talk in the next few slides about robot soccer, and Jeffrey mentioned that that's something I've worked on a lot. These are some old Sony IBOs from the older version playing soccer completely autonomously. So they had a camera. They were sensing. They were deciding what to do. They were acting. That was a goal that was scored by one of my teams back in I think 2004 or 2005 or so. And then when that version of the IBO was discontinued, there's now a new version. We moved to these robots called Nows, but made by a company called SoftBank, originally Aldebaran. And this is a clip of our robots. Ours are the ones with their hands behind their backs. Playing in the finals of a robot soccer competition. This is actually from 2012. It was held in Mexico City, and we were playing against a team from the University of Bremen in Germany that had won the competition the year before. And here you see our robot going in on a breakaway. And when again, you have to keep in mind that we had programmed the robot, but all we could do here was watch it. Nobody was remote controlling it. It had to sense, decide, and act. That was the first goal in the game, which we ended up going on to win 4-2, and so we became the RoboCup Standard Platform League champions that year. When we came back to the University of Texas, they lit the tower orange for us, which they usually do when the football team wins. So we were very honored. But so that is robot soccer has been one of my research problems that's motivated research. And I will talk a little bit more about that. Another problem that we're actively working on here at UT Austin is what I call the building-wide intelligence problem. And so if you come to our building, at least when it's not in the time of the pandemic, when it's open, that you can often see a robot like this one just wandering around the hallway. And you don't have to ask us for a demo. It's just on all day. And our goal is to try to make it become a part of the social fabric of the building, that people expect it to be there. The robot knows when people want to be left alone, when they want to be entertained, when they want to be helped. This particular video is joint research with a colleague of mine, Ray Mooney, and this is a former PhD student that of Ray's, Jesse Thomason. And in this case, the robot was learning how to interpret natural language based on engaging in dialogues with people. And over the course of time, it got better and better at understanding what people wanted the robot to do. And so this is ongoing research. We have the robot trying to recognize people's activities. We have multiple robots, again, trying to just become expected parts of the building, which is a sort of a grand challenge for us. And of course, for many people in AI these days, autonomous driving is a huge challenge and inspiration. This is a picture of the car that I had in the DARPA Urban Challenge back in 2007 that went to the final event in California, and it was able to drive by itself. I can show a brief clip of that. Our car is the one in the back here. There's nobody inside at this time, and it had to find a gap in traffic. And then once there was a gap in traffic, it had to turn left, and it completed sort of 8 loops through this track in the course of about 20 minutes. We don't have this car anymore. All the car companies are investing a lot in what the world will look like when all the cars on the road are autonomous, but we do still think about what the world will look like when all the cars are autonomous. And so this is a multi-agent systems simulation that we built actually more than 15 years ago now, but to envision what an intersection could look like. Would we need traffic signals and stop signs, or could we have cars coordinating with one another to get through an intersection? And this is, in this case, what's happening is the cars that are white have called ahead to get a reservation in space-time through the intersection. And the ones that are in yellow don't yet have a reservation, but as soon as they turn white, they have a guaranteed path through the intersection that won't collide with the other cars. So I could give a 1-hour talk on any of these applications. They've all sort of inspired research on each of the, on this question, and new algorithms in artificial intelligence. And to me, they're all super pertinent because they all involve multiple agents and learning and dynamism. The world is changing, it's not static. And that's what I mean by dynamic domains here. So that's just sort of a window into the kinds of things that that drive me. I said I would tell you a little bit more about RoboCup soccer. I'm actually currently the president of the International RoboCup Federation, and we have actually a very clearly stated long-term goal, one that was coined by the founder of RoboCup, Hiroaki Kitano, and that's by the year 2050. To create a team of humanoid robots that can beat the best World Cup champions on a real soccer field. So, it's good to be ambitious. I have no idea if this is going to be possible. There's still a long time to go, but we've been making a lot of progress. There's a long ways to go. There's still a long time to go. I'd say we're still, in the relatively early stages. People started working on this about 20 years ago. So, the clock is ticking, but it's a great challenge problem for AI, and really epitomizes this idea that I was talking about of good problems producing good science. It forces us to build complete systems right from the start, and it's a very inspiring domain. People love working on it. As Jeffrey said, he came into the and saw my team in action several years ago. There's several different leagues in RoboCup. Of different sizes, but the thing that unifies them is that there's always they're always autonomous. There's never a person controlling the robots. And so to get a sense of the progress, if you look back at the first RoboCup competitions in 1997 and 98, it's actually very painful for me to look at now, because the robots are falling over. They're running into walls. It's not shown here, but sometimes they actually caught on fire. But it was a big, actually, at that time, it was a big success to get robots that could sense, decide, and act, that could actually do the whole thing. Most people at the time in AI research were still picking one single part of the problem, either the vision problem or the locomotion problem. They weren't putting it all together. And so RoboCup was one of the first challenges that forced us to put all of these things together. And now if you jump forwards 10 years from that, or a little less than 10 years from that, you can see the progress. The robots are now much more individually capable. They're moving much more quickly. They're starting to show teamwork. They're starting to show passing. This is even still 15 years ago now, and there's been continued progress since then. It was the beginning of the penalty shot, the humanoid league, so they just had a penalty shot competition. So there you see the goalie trying to make a save and failing in the bottom right corner. But it's it was progress, and this is really, those robots weren't all my own. It was people from around the world all working on this common challenge and continuing to. And just to give you a little more insight into it, my team, UT Austin Villa, has actually been doing very best recently in the 3D simulation league. So in addition to the real robot leagues, there's a simulation league. We've won 8 of the last 9 years, and this is what that looks like. It looks a little bit like a video game. The robots are in a sort of a physically realistic simulator. There's gravity, so just getting them to stand up without falling over can be difficult. Getting them to walk and kick. You've got 11 robots on each team, and critically, each robot is controlled by a completely separate program. This is one of my favorite clips coming up here, where our robot was able to kick the ball right through the legs of the opponent and into the goal, past the goalie. That wasn't planned. That was just lucky. But what was planned was the learned skills, the learning how to walk, learning how to kick, figuring out where to position yourself. And again, there was a whole bunch of new machine learning algorithms that were developed because of this challenge that we're a part of. So RoboCup isn't just about soccer. There's aspects of RoboCup as well. It's sort of meant to be a place for grand challenges in robotics, artificial intelligence, and multi-agent systems. There's also a RoboCup Rescue. Some of you may actually know of RoboCup Junior for high school students, and then there's RoboCup at Home, which is very connected to the building-wide intelligence project that I showed you about, of our robots wandering in the hallways. And in fact, we have a robot like this one, the Toyota HSR robot, that as a part of the RoboCup at Home competition, it has to do things like unloading groceries from a table onto a shelf, or in the case of this video, taking out the trash. So it has to take the lid off of the garbage. It has to see it. It has to figure out, use its gripper to manipulate picking up the trash and moving it outside. And there's other things that are a part of this competition, being able to communicate in natural language with people, do activity recognition. It's a very, again, inspiring domain. One of the challenges is actually to go take your robot to a restaurant, a real restaurant that it's never seen before. Look for people who are waving their hands at to get service. Go over to them, talk to them, and ask them what item do they want. And then understanding if they say Pringles, or if they say I want a Sprite, it has to go to the table, pick up the right item, and bring it to them. And so to be able to do this, again, we have to put all of these pieces together: the natural language processing, the perception, the navigation, all of these. So at this point, I'm going to ask you, and I think Jeffrey's going to help moderate. You might have to answer in the chat. But if I were to give you one of these robots, the one that I showed before, this Aldebaran Now robot that was in this video, and I said, you're going to have this team of robots. There'll be 4 or 5 on the team, and it's basically a computer. Think of it as a computer with a camera. The main difference is it has legs and arms, but it's got the processor on board. It can do that. If I were to give that to you and say it's your job to program it to play soccer, what would you do? If you had a class of people trying to work on this, what are the sub problems? How would you decompose the problem? What are the tasks that you would need to try to get the robot to do? So I'm going to pause here and let Jeffrey try to collect some of the ideas.
So one I've gotten from the audience right now is instantly search up a pre-trained model for the task. Standing up when they fall down, vision, navigation.
Good.
Teamwork, noticing opponents, programming it to kick the ball, recognition, standing up, walking, kicking, planning, strategy, ball detection, reflexes, teamwork, blocking the goal, vision. I'm getting a lot of vision and teamwork.
Yeah, exactly. So that's great. That was probably the most rapid fire I've ever gotten an answer to this, with so many people typing at the same time. So that's fantastic, and that's right. There's and all of these things are things that we have had to program. And so I'm going to give you in the next few minutes, I'm going to tell you a little bit about especially the vision. How do we get the robot to perceive the environment? I'm going to tell you a little bit about the movement, right, that people talked about. The robot has to be able to get from here to there, and that's another skill. Kicking is also a skill like that. The teamwork the multi-agent systems aspect. And I'm going to especially try to give you insight into the decision making, the learning how to make decisions. That's the reinforcement learning. And so I'll show, I think this bodes well for the activity that's about to come up as when we get there. So one of the things that you said, you got a lot of vision. A lot of people said vision. And in fact, that is one of the challenges. And it's really actually important to recognize, what does the world look like from the camera of the robot when it's playing soccer. So here's actually, this is showing you the viewpoint of a robot as it's walking up to the ball. This is actually from one of the IBO robots, so one of the dog robots. And notice that, a few things here. First of all, that the world is bouncing around all over the place, right? Because the robot's walking, the camera's jostling around. There's, so the ball isn't even in the vision, in the camera all the time. And so, this is a typical still shot, but you have to put them together coming in at 30 frames per second. And in particular, what is each of these images, how is it actually represented to the computer? It's actually just, if you open up an image on your cell phone, a picture, it's represented as just a bunch of dots, a bunch of very small pixels that each have a red, green, and blue value, an RGB, and each number being from 0 to 255. So like exactly where my arrow is now, there's a number that means red from 0 to 255, green from 0 to 255, and blue from 0 to 255. And of course, these ones will be mostly green, these ones will be mostly red, but there's hundreds and hundreds of pixels coming in 30 times a second. And we need to write a computer program. In this case, it was written in C++, to try to identify where's the ball, where's the goal, where are the lines, where's the robot on the field, the localization problem, figuring out where it is. All of these things are challenges. And in particular, the orange isn't a fixed set of numbers. If the lights change, if the sun comes out, then the pixel that means orange in this image might be it might mean the color yellow in a different image. So trying to put all of this together and to be able to have the robot understand for itself what colors, what pixel values mean different colors is a challenge. And so one of the research problems that one of my PhD students, the way he approached this, was to have the robot walk around the field and identify for itself what means green and what means white and what means yellow, based on its knowledge of the fact that there's a yellow rectangle at one end and a blue rectangle at the other end. And so in different lighting conditions, it could figure out for itself how to do that mapping from pixels to from numbers to colors. So this is some of the challenges we've had to address with robot vision. Another problem that people mentioned was walking, locomotion. How does the robot get from here to there? We actually, much more recently than that, a PhD student of mine, Josiah Hanna, introduced a way to get the fastest walking robots using a method that we introduced called grounded simulation learning. And I'm not going to go into the details here, but it's basically, we do most of the learning in a simulator, the one I showed you before. And we use a little bit of data from the real world to try to make the simulator more like the real world, and then improve our walk and then repeat in this sort of cycle that's illustrated here. And so what we did is we started from a walk that's being shown here was the fastest that anybody had gotten this robot to walk previously. This was a group from the University of New South Wales that also participates in the RoboCup competition. They had it walking at 19.3 centimeters per second. With our using our learning method in this grounded simulator, through one iteration, we were able to get this walk here that's going significantly faster, 26.3 centimeters per second. And then we took a second time through this iteration, through this loop, and we're able to get a walk that was 43% faster than the walk we started with through learning. And it was the fastest known stable walk on this robot at the time. So that was a robot control problem that was very much inspired by this robot soccer challenge. I'm going to talk about the teamwork and the multi-agent systems a little bit later, but the other thing that was sort of common in the chat was the idea of decision making, of deciding what to do, and the robot trying to learn when should it pass the ball, when should it dribble the ball, when should it shoot the ball. That's something that we've used a machine learning method known as reinforcement learning to try to do. And to give you a sense of what reinforcement learning is like, I'm going to try to give you a perspective of being a reinforcement learner, a reinforcement learning agent. And so Jeffrey's going to help me with this as well. Your job as a group is going to be to act as a learning agent. You have 3 actions that you can take. So I'm telling you that you can either wave or stand or clap at any given point. And if we were in a room together, I would actually point at one of you and say, okay, now what do you want to do? Do you want to wave, stand, or clap? The observations you're going to get are colors and a reward signal. And your job is going to be to find an optimal policy. And so what is a policy? It's a way of selecting actions that gets you the most reward. So your job is going to be to try to get the biggest, the highest reward as you go. Okay, so we're now going down to this environment. You see green, so that your observation is the color here on the side. And I'm going to type in either wave, stand, or clap on in the terminal window here, and that will give you a new observation and also a reward. So Jeffrey, either pick for yourself or take input from the audience.
All right, first person to stand.
Okay, so you stood, and by the way, you may, if you're following along at home, you may want to have a paper and pencil in front of you, because you're going to have to try to figure out, you're supposed to be learning what to do here. So right, you now see black. Go ahead.
I'm now seeing a lot of waves. So
okay, so wave gets us to green, and your reward is still 0.
A lot of claps now.
Okay, clap goes to purple, reward of 0.
I'm seeing a mix now, but I'm just gonna go with stand.
Okay, stand goes to blue. We're still a reward of 0, and you may want to do it a little bit rapid fire at the beginning, and then think about it a little more as we go.
I'm just gonna read the chat's blowing up. So
okay.
Clap.
Okay, clap goes to brown with a reward of 0.
Wave.
Wave. White with a reward of 0. So nothing super interesting happening yet.
Wave.
Wave again. Brown with a reward of 0.
Stand.
Okay. White with a reward of 0.
Clap.
Yellow with a reward of -3. So that's the first reward signal you've seen, and it's been negative.
Nice. Okay, a lot of stuff in the chat. Lots of waves now.
Okay, wave, pink. You got another negative reward of -1, so you're at -4 now.
There's a ton of messages. Wave.
You have the so I did wave and it stayed at pink, and you got another -1. You're the arbiter, so you can decide if you want to ignore some of them for a while. You can, and then go back to the chat later.
Wave does not seem to be going in a good direction, so let's go with stand.
Stand goes to yellow with a reward of 0.
I've seen a suggestion for someone that says to keep trying the same thing each time, so let's try it. So let's try stand again.
Okay, stand goes to cyan with a reward of -1.
I think I'm seeing a lot of claps now.
Okay, clap goes to cyan again with a reward of -1.
Not doing a good job of this, but walk.
Wave, you mean? Wave goes to yellow with a reward of 0.
Wave. Yeah.
Okay, you're at yellow.
Clap.
Clap. A reward of 10. And back to green.
All right.
So now you're doing a little better. You're in positive territory. And this is a state you've definitely been to. This is, I'll remind you, this is a state that we started at, which was green, or an observation anyway that you started in, which was green. So now what?
I'm seeing a lot of waves again.
Okay, goes to red with a reward of 0.
I'm seeing a lot of, all right, stand.
Stand, green with a reward of 0.
Clap.
Clap, purple with reward of 0.
Wave.
Blue with reward of 0.
The audience seems split, so.
So you get to choose.
All right, clap.
Brown with reward of 0.
Stand.
Stand goes to white with reward of 0.
Wave.
Brown with reward of 0.
I think someone tried, wants to try clap, stand, wave, so.
Okay, let's try clap, stand, wave. So clap goes to pink with reward of 2. So that's positive. And then you want to stand from there.
Yeah.
So that goes to yellow with reward of 0. And then still want to wave from there.
Yeah.
Okay, pink with reward of -1.
All right. Seeing a lot of claps now.
Okay, clap stays at pink with reward of -1.
So I see some people suggesting clap, stand, clap. So.
Okay, so clap stays at pink with reward of -1. Then stand goes to yellow with reward of 0. And then you wanted to, from here, clap again?
Yes.
And so clap, reward of 10 to green.
All right.
Now what? You're in positive territory still.
Seeing a lot of waves in the chat, so.
Okay, so wave goes to red with reward of 0. Now what?
People want to keep trying clap, stand, clap, I believe, so.
Okay, so clap goes to blue with reward of 0. Stand goes to purple with reward of 0. Clap goes to white with reward of 0.
All right. People want to try clap, wave, clap again.
Okay, here we go. Clap to yellow. From yellow, do we want to? Do you want to keep doing wave from here?
I think so. The audience
Okay.
is very split, so.
Wave says wave goes to pink, which is a reward of -1, and then clap again stays at pink with reward -1 again.
There's all right. I think
So here's, I'll take
there's
you
a lot
to,
of mixed
I'll do
answers.
a stand. What about if I did a stand, which got a reward of 0 and took us to yellow? What do people think we should do from yellow?
It's
Okay,
looks like a split of clap and wave. Yeah.
All right. Well, let's take the. I'm seeing more claps, so let's do a clap, which gets reward of 10 and goes to green. Okay. So I saw somebody say that yellow plus clap gives a reward of 10. Okay. So then what are you going to do next? Let's do it. Let's spend a little bit more time on this, not much more, and then we'll talk about what's going on here.
All right, so the color is green. So
Yeah.
if anyone in the chat remembers what we did last green, then
I'm seeing a lot of people say clap. So I'm going to clap from here, which goes to purple. Somebody's saying to clap a lot. So I'll try that theory. Purple goes, so clap went to purple. Clap went to white with reward of 0. Clapping from there goes to yellow with a reward of -3. And then clap from there goes to green. So I'm going to stop this activity now. I think you get the sense. It's a little hard to do this over Zoom. But the question I want to ask you is how did you do it? And again, if we were in a room together, I'd point to somebody and say, what was going through your head as you were doing this? And in particular, what's your policy and what do you think the world looks like? So what you were really doing was being a reinforcement learning agent. If we did this long enough, you would start getting a sense of when I see yellow, I want to clap. And I think that is something that a few people wrote. But then you might say, okay, from the beginning, I want to wave first and then stand. We probably didn't do this long enough for you to actually understand what the environment looks like. So I'm going to give you the answer of what it was. It looked like this. So every time you were actually in a 4x3 grid, and every time you stood, you went up. Every time you waved, you went down. Every time you clapped, you went to the right. There were some rewards here, a -3 for this one, a +10 for yellow and clapping and going back, and a -1 every time you bumped into the wall. So we didn't do this for long enough for you to figure this out, but this is what you would need to do if you're a reinforcement learning agent. You would know what your actions are, you'd see observations, and you'd have to try to figure out how to improve your policy over time. And so that's one of the things we do in artificial intelligence and reinforcement learning is try to write programs that will learn from their own experience how to get better at acting in their environment. And in particular, I'm gonna say how we can formalize what just happened. I know it was, a lot of you in the chat, I was seeing you were getting frustrated that it wasn't, it was going a little slowly, you weren't learning enough yet. But in general, if you think about that activity you went through, what was happening? There were some things you knew, right? I told you at the beginning that your observations would be colors, that your rewards would be real numbers, that your actions were wave, stand, and clap. You saw the observations, actions, and rewards in a sequence, right? Observation 0 was a color, then an action, then a reward. There were some things that were unknown, like what's the state space? I told you in the end that it was a 4x3 grid, but you didn't know that. You didn't know when you were in a state and you took an action, what reward you would get. You started learning that when you were in yellow, when you saw yellow and clapped, you would get a 10, and probably you learned some other things. But maybe in the state you would get an observation, and in particular there were multiple states that would give you the same observation, which made it tricky, right? There were two different states that were blue and 2 that were brown. And there was also a transition function. When you were in a state and you took an action, you would end up in another state, and you had to learn about that as well. And so really what was happening was that there was a state that you didn't see, an observation that you did see, an action that you selected, a reward that you received, and you were trying to figure out these functions, to figure out the transition function, the reward function, the observation function, and to come up with the best policy. So that's in reinforcement learning, we're trying to write computer programs that can do what you just did. And so in my lab, we've been working on trying to do this in more complex domains, in robot soccer, for instance, figuring out when to pass the ball, when to kick the ball. Sometimes just from experience, like you were doing right then, but also sometimes through human interaction, like demonstrations or positive, negative feedback. So here's a domain that we use, the game of Tetris at one point, where I don't have that video showing here, but we. Let's see if this one works. You can have a a couple of my links are broken here, but what we did is we had a robot learning to play the game of Tetris by a person just saying good move or bad move after each time a brick got placed, or learning from demonstration, having a person demonstrate what we want the robot to do, and then have it the robot try to copy it. We also do research on transfer learning and reinforcement learning, which is like if you're trying to learn how to play the game of chess, which is sort of a reinforcement learning problem. You learn, how to move pieces to try to maximize the chances that you'll win. You might want to first learn how to play checkers or tic-tac-toe and use what you learn there to get better at learning other things. So that's also a challenge that we try to address in reinforcement learning. I have a current PhD student who's working on curriculum learning, trying to figure out what should be those tasks to practice on. So these are some of the things that we do reinforcement learning on, including trying to get an autonomous car to drive. So in this particular video, we had a car trying to learn when to press the accelerator and when to press the brakes so that it would get to a particular speed, right? So now its observation is how, instead of colors, like in your exercise, its observations were how fast it was going. And instead of the actions being stand, clap, or wave, the actions were press the accelerator more or press the brake, but it's the same idea. It's learning from experience what the effects of its actions are. And so that's what reinforcement learning is all about. So I said I'd also talk a little bit about multi-agent systems. That's the teamwork part of robot soccer. And one of the things we work on a lot is motivated again by soccer, is trying to create good teammates. And in particular, one thing that I've been really fascinated by lately is trying to create good, what we call ad hoc team players. So a person can go and play a pickup soccer game with people they've never seen before, right? They can go and they know, every person knows how to play the game, but they've never acted as a team before. And people can just on the fly figure out how to be a team. We're trying to figure out what are the algorithms to allow robots to do that. Either for soccer or for things like disaster rescue. If I have a robot, if there's an earthquake and we all have robots that can rescue and identify victims, we don't want to have to all bring them and then reprogram them to work as a team. We want them to figure out on the fly how they can work as a team. And so that's one of the challenges in multi-agent systems. It's trying to create a good team player. And so we introduced this as a challenge, another sort of grand challenge problem for AI, and we've tried working on it in contexts like this, where a domain, this is called the predator-prey domain, where these 4 red agents are trying to surround the green agent, the prey, but in a way where they haven't practiced together. They have to figure out on the fly how to work with teammates they've never worked with before. And similarly, how can we get soccer players to work together? Another instance where we've looked at this is a student of mine, Katie Genter, is her PhD thesis looked at if you have a whole bunch of simulated birds where each one decides which direction to fly based on where its neighbors are flying. We asked the question, if we put a few pink birds that we control into a flock of gray birds that are just acting by themselves, can we figure out how to move these pink birds so that we can actually control the whole flock? So you could imagine putting in some robot birds into a flock of real birds, and then just by controlling those, getting them to fly around an airport or something like that. And so that's an example of multi-agent systems and ad hoc teamwork. And as you might not be surprised that we've also taken a look at this in the robot soccer competitions as well, where we've had one robot from every team trying to work together, even though they weren't programmed to work together. And so so we do that. We have pickup robot soccer games. So this talk has been to sort of give you a window into the AI research that's been motivated by my research problem, the one that I introduced at the beginning of the talk. Again, it's to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains. It touches on several different sub-areas of artificial intelligence as shown here. So where does that leave us now before wrapping up? Well, for me, I'm left with still lots of open research challenges. I said I've been working towards this for the past 3 decades or so. And there's still lots more to do. There's no danger that we're going to solve this problem of creating fully intelligent agents that are robust in the real world anytime soon. So I'm pursuing this as a professor of computer science at UT Austin. as the director of Texas Robotics, as the president of RoboCup, and also now executive director of Sony AI America. So just to cycle through some of those pages where you can get information. This is our computer science page at UT Austin. Texas Robotics includes roboticists from also from other roboticists from computer science, but also mechanical engineering, electrical engineering, and aerospace engineering, all people trying to create intelligent robots. The RoboCup Federation is people around the world all working on this robot soccer challenge. And at Sony AI, we're working towards trying to figure out ways that we can use artificial intelligence to enhance human creativity. And so these are all aspects of this challenge of creating fully intelligent agents. Where does it leave you? And I know there's not only high school students in the audience, but I'm talking especially to the high school students and early college students. You're at a point where you have lots of choices and opportunities. And things like, where will you go to college? What will you study? What will your lifelong challenge be? And in some sense, I hope I inspire some of you to be interested, in the problems that I'm interested in within artificial intelligence. But more importantly, I hope that I inspire you to figure out and to think about what is the challenge that's going to drive you. Maybe it's not, computer science. Maybe it's not art. Maybe it's maybe it's the nature of the universe, or how it originated, or how life originated, or maybe it's one of the psychology or neurosciences approaches to the nature of intelligence, or maybe it's a completely different question. But it's now is the time for you to be exploring this and thinking about it, and with the whole world of possibilities in front of you, and hopefully picking something that will sustain your interest through your whole career. So that's me and you. Where are we in the field of AI? AI right now is really thriving. It's a big uptick in the sort of the cycle of it. But there are some concerns. So I just want to close with giving a little bit of my, and I did want to show just also some websites pertinent to your decisions. At UT Austin here, we do have, if you do come here, we do have what's known as a freshman research initiative that allows, even as a freshman in college, to start getting involved in research, including in my lab, working on autonomous intelligent robots. And for those of you particularly interested in computer science, we have a fantastic computer science department, including an honors program called Turing Scholars, with some of the best opportunities for computer science research in the world. But coming back to this, where we are for AI as a field, I'm going to just show a series of sort of notional graphs here. There's no y-axis deliberately. It's meant to be just sort of vague progress in the field of AI, and the x-axis is years, where AI sort of started in 1950. And from my perspective, the field has been really advancing in a very healthy and steady way, with gradual advances, sometimes at a slightly higher slope than others, sometimes with a little bit of a lull, but really through sustained effort of a very large and interested community, people have been making a lot of great progress. Unfortunately, the perception of AI is not at all like this. The perception of AI is much more bimodal. There's times when people think that AI is a huge success, that it's going to solve all the world's problems, become way overly optimistic. And there's other times when people have become much more pessimistic about AI, where it didn't live up to its promise. We sort of call those the AI winter in the field. And there have been some in the 1970s, and even in the sort of early 2000s and late 1990s, there was sort of an AI winter. We're certainly now in an uptick. We don't even know if it's, we sometimes debate about whether this is the spring or the summer for AI. But there is sort of, there's from my point of view, there's very much overinflated perceptions. There's been a lot of great successes in AI. But there's this tendency of people to think, well, a computer program can beat the world champion in Go, for example. But and therefore it can do all these other things as well. You just take that magic of and sprinkle it on other things and make them intelligent. And that's very much not the case. We need different research algorithms to have programs that can play soccer, drive cars, do your taxes, bid in auctions. All these different things require different algorithms that can learn from one another, and can build upon one another. But there's not really any silver bullet. And right now, I think a lot of people, that's sort of the biggest myth of artificial intelligence, is that you can just sort of advance in one problem and it automatically applies to everything else. So there is some uncertainty of where we're going to go in the future, whether we're going to keep on an uptick or whether things will slow down. I have no question that that we're going to keep making progress, especially with so many people interested and a lot of resources. But history shows us that that we're not going to live up to the expectations right now. And it's important to try to be as realistic as possible. Typically, the higher people get, the more inflated the expectations get, the bigger they are, the more they're disappointed by finding out that the programs aren't quite as intelligent as they thought in the end. And so I hope one thing that you take away from this talk is that AI is not magic, that it's a lot of different algorithms and subfields that all need to be put together, and that we still have a long way to go. So the last slide I want to show is in a talk like this, if you're thinking about going into AI, I did start the talk by saying our goal is to create robust, fully autonomous agents in the real world. An important question is what happens when we achieve this goal, or if we achieve this goal. Will we have a utopian world like that's often portrayed in the Jetsons, or will we have a more dystopian world, as the movies sometimes like to show? In practice, probably neither extreme, although that's what makes the good story. Science fiction is usually about either the wonderful sort of world-saving possibilities or the doomsday prophecies. One thing I like to ask, and I think it's incumbent upon anybody who goes into artificial intelligence to think about: are you making the world a better place? Is our AI technologies improving things or making things worse? And one way I like to think about that is asking: would you rather live in a world or be born 50 years before you were born, or would you rather be born 50 years after you were born? And that's not actually an easy question for a lot of people. There's who knows what the world will be like in 50 years in the future. We know that there's in many ways things are better than they were 50 years ago, but in some other ways there's very compelling cases that things are worse. So a question is which way, if you're not allowed to stay where you are, which way would you go? Personally, and for people in computer science, I think many people are very quick. I'm only doing what I'm doing because I'm very excited about the possibilities of AI into the future. I think AI can be part of the solutions to some of the problems, but it isn't clear, and it's something worth thinking about. Is technology making the world a better place? And some of the activities that I've been a part of that think about this actively are the 100-year study on artificial intelligence. If this is a question that entices you, I strongly encourage you to read a report that I co-authored with some of my colleagues a few years ago that asks these kinds of questions. In particular, and there's also an effort here at UT Austin called Good Systems, where we ask, what should we build? We don't just build something because you can. Think about what the effects will be on society, and think twice, and try to figure out what are going to be the impacts. And that's one thing I forgot I wanted to mention on this slide for where you are now. People often ask me, what do you need to do to get involved in the kinds of research that I do? There's no doubt that you need to do well in your math and science classes, but AI is becoming more and more a cross-disciplinary field that requires really strong background in the liberal arts as well, very strong writing skills and presentation skills. Really, you need to be a very well-rounded and have sort of be educated in the whole aspects of thinking and writing and presenting and reasoning, to be able to have impact in this field. So I would encourage you to think about that as you decide where do you want to go to college, where do you want to study, and what your challenge will be. So with that, I know I've taken, Jeffrey, I don't know what the protocol is here. I've gone for about an hour. I'm happy to stick around and take questions if people would like to ask.
Yeah, all right. So I'm gonna just first start with the questions on Slido. There's quite a few, so I'm just gonna go down through that list, and then
Sure.
yeah. Also, everyone who's in the audience, yeah, feel free. You can still submit questions now. So, I guess just starting at the top, what are some ways high school students can get involved in the AI field?
Great. So I think I touched on that a little bit. Like I say, if you come to UT Austin, there's the Turing Scholars and the Freshman Research Initiative. Most universities these days do have programs in computer science and in artificial intelligence. But really, it's the thing I was talking about at the end here, is that you're at a point right now where you can shore up all of your skills, and artificial intelligence absolutely needs, to get involved. You need to be able to have good communication skills in terms of oral presentation, in terms of writing, in terms of communicating. If you make an algorithmic discovery, but you're not able to tell the world about it in a way that they understand it, it's not going to have any impact. And so, so that's, the English side of things, the language side of things, and then the tools that we use are mathematics, including linear algebra, including calculus and differentiation and gradients, and so there's a lot of sort of basic skills that are needed. But then I think go and take introductory courses, and then start reading about the literature, but look for research opportunities. I know at UT Austin at least, and I think in many universities around the world, you can, as an undergraduate, go in and start getting involved in research while you're taking classes, and that's the best way to get a taste of it.
All right. I guess the next most liked question is just, what's the largest evolution in the field of AI in the 30-odd years that you've been in the field?
Yeah, that's a great question. And that's actually why I show this slide. I think, there haven't been, there's been a perception of sort of big jumps, but really it's been gradual, steady progress. And, broadly speaking, people talk about there being sort of three periods of AI research. One is one when it was dominated by sort of symbolic reasoning, as it's called, which is sort of logic-based and planning. That was sort of the dominant paradigm in the early years. And then in around the 1990s and 2000s, what became dominant was what's known as probabilistic reasoning, Bayesian reasoning. And so instead of thinking of the world as sort of, so the symbolic reasoning would say, this is a cup, the cup is on the table. If I want to plan to get the cup into the air, I need to move my hand to pick it up and lift it. But not really thinking about uncertainty, about, well, what happens if my hand misses the cup, or if it spills, or if it's heavier than I think. So that's what probabilistic reasoning allowed us to do. And then most recently, there's been a big emergence of the power of neural networks and machine learning, that have, which sort of, I think to the outside has seemed very sudden, but really people have been working on neural networks for decades as well. In fact, my undergraduate research project, I told you, you should get involved in research when you're an undergrad. I was at the University of Chicago getting a liberal arts education as an undergrad, but did research in computer science. And my project was to implement a neural network. And that was back in the early 1990s, 1992, 1993. So it's not really, the concept of neural networks isn't new, but the power of them has recently been, sort of exploded as we got into really big data sets and really big computation. And so that's, become a dominant paradigm. In my view, though, what we really need is to integrate all three of these, the logical symbolic reasoning, the probabilistic reasoning, and the machine learning and neural networks. And so that's sort of, with a really broad strokes, the the kinds of changes that have happened in the field. There's been big landmarks that have been very impressive, things like beating the human chess champion Garry Kasparov in 1998, winning at Jeopardy. We hope that robot soccer will be another one of those landmarks. But those landmarks are not really due to sort of quantum leaps in the algorithms. It's more just everything comes together, and now you can finally do something that you hadn't been able to do before. And so to me, that's the story of this field, this sort of gradual, community-long, slow and difficult but exciting progress in lots of different areas.
All right, thank you. I think next, I think there's a few kind of more detailed questions about robot soccer. So I think one person asked, how long does it take to make one of the robot soccer players?
Okay, that depends. So if I go back to the, I'll go back to the slide with the different robot soccer leagues. So each of those is different. The ones that I've participated in, so the small size league here and the mid-size league, people do build their own robots, their hardware. There's also the ones that I've participated in have been the standard platform leagues, where we buy the robots and everybody has exactly the same robot. So it's more of a who can program them better. So there, it's not the challenge of building the robot, it's a challenge of programming the robot. But it usually takes us, to get to the level of being able to win one of these competitions, takes us usually, a couple of several years of effort. With of multiple people. Usually by going 1 year and not doing very well, and then learning from the other teams and coming back and improving things. The simulation league, I said we've won 8 out of the last 9 years, but before that we had 4 or 5 years where we didn't do very well, and gradually improved our code and had some machine learning breakthroughs. So it's really it's not the kind of thing you can just go and do as a 1 semester project or as a class project to get to the top levels. But if you go into the simulation league, you can actually start making progress by downloading existing solutions, and at least start playing around with it without too much effort. So it really depends on each of these. But it is it's not designed to be an easy problem. It's it's something that we have to put a lot of time and effort into, but we do it as sort of a labor of love. It's very exciting, it's fun, and the students who are working on it end up I think seeing it as a privilege in some sense to be able to work on these robots and try to take them into this sort of international event where everybody's trying to work towards the same goal. So it's not a crisp answer of how long it takes, because there isn't one. It's it depends on the league, it depends on who you're working with, and it depends on what your starting point is.
I think there's also a few more questions about your robot soccer teams. So one is, generally do these robot soccer teams open source their code, or is it something that's more closed because it is a competition?
Yeah, that's a great question. So one thing that we've been committed to at RoboCup is that it is a competition, but there's no monetary prizes. The only prize you get for winning is the ability to disseminate your algorithms and your code, to publish your research. And so there's a strong motivation for people to share, to open source their code. Typically, it's not a requirement. What we do require is that teams share their binaries if it's in the simulation league, so that other teams can practice against them. We do require that people write technical reports about the work that they did. But typically the winners of the leagues, especially in the standard platform league where the code can be shared, do make their code available, and teams do build upon each other's code. So it's I think if there were $1 million prize for winning each year, then people probably would keep it very secret. But really, the prize for winning is notoriety, and the way to get that notoriety is to make your algorithms and your code as available as possible to other people, so that they'll use it, build it, cite it, talk about it, and that's been a really important part of the RoboCup culture.
Yeah, I guess a few more along this vein. So how much processing power usually do these robots have, considering that they have to be fairly mobile and
Yeah. So when I'm pretty when I say that these robots are sort of like laptops with legs, I'm saying that pretty literally. They have a processor on board that is that's usually not quite the cutting edge laptop processor, but maybe like a processor you could have gotten in a laptop 2 or 3 years ago. Um, the these robots, like the ones that we have driving around our hallways, they literally just have a modern laptop sitting on top of them that does all their computing. So it's there is limited processing in the from the point of view of you're trying to take in images that are very high resolution, multiple times per second, and so that becomes a bottleneck. You don't have like an array of processors, but it's probably the processing on them is probably as strong as most of the laptops you're all watching or computers that you're watching me on right now. So it's gigahertz processors. The one thing that we don't have on these now robots is there's no GPU right now. But on the robots that people build themselves, they can put on any kind of processing they want. I'd also say the small size leagues they're a little bit more limited in what you can put, because the robots are smaller. But once you get to the bigger robots, they're basically modern laptops.
yeah. And then I guess final question on like robot soccer is someone was wondering, do these robot teams form hierarchies? Like, is there a robot like team captain really, or is it more
Yeah,
decentralized?
yeah, that's a good question. So they are decentralized, except for the small side league. They have an overhead camera that can see all the robots and then sends commands to all of them. So that can be more centralized. But all the other ones, it's a separate process controlling each robot, but they do have communication. And so yeah, that question sort of has that insight that sometimes there's a single robot, like sometimes the goalie, which can see the whole field, will tell the robots, give them some ideas of which one should go where. But usually it's much more distributed. The robots will tell each other which one is gonna go to the ball and where they're gonna move to pass. So we do put communication in. Sometimes there is hierarchy where we think of a team captain that's doing more of the decision making. But more often than not, we try to make them as interchangeable as possible, so that if any robot breaks or has to come off the field, that they're all capable of doing everything they need to. But that's part of the multi-agent systems challenge, is how are you going to organize the team? How are you going to make sure they're not all going to the ball at the same time? How are you going to break up the conflicts? And that's exactly, those are the kinds of things we think about in multi-agent systems.
All right, so there's still a lot of questions, but I think in the interest of time, we'll just wrap up with just one final question, which will
Okay.
be more, I guess, general. So I think this is a two-part question, really. So the first is, how do you think the future of AI is? You talked briefly about this, but what sort of direction do you think is growing? Do you think growth will start to plateau, or do you think this is only really the beginning? And I guess more specifically, do you think you can achieve the goal of ultimately by 2050 being competitive with World Cup players?
Yeah. So great question. So where's the field going to go? I really don't know. That's why I put this uncertainty slide. Is I've been surprised many times in my career already about what things that I thought were going to be easy have been hard. Things that I thought would be hard have been easier. One of the great things is one way sometimes people talk about artificial intelligence is that it's the science or practice of trying to get computers to do things they can't do yet. And that's sort of a funny definition, in the sense of, as soon as computers can do it, then it's not AI anymore. Now it's engineering, and then you have to move on to the next thing. And but that's sort of what it is, often what it's about. If processors get faster and solve a problem that used to be AI, now there's something new that's just outside the reach of just using a brute force processing, and that becomes the challenge for AI. And so I think there's so many things that we can't yet do, although it's sometimes appealing to think of, oh, well, neural networks are so able to do this, so many impressive things. And they can do some very impressive things. There's still so many things that they can't do. That are going to require, major breakthroughs still. Like I say, there's no risk that we're going to solve this challenge, I think, anytime during my career. And I really expect to be surprised. I think, some of the biggest current challenges are robot manipulation, getting robots to be able to pick things up. And, we're pretty good at getting robots to move around, but getting them to handle things dexterously, people are still working on, and, sort of move quickly and agilely. And then really, despite the, in the news, things like GPT-3 that show remarkable language abilities, the ability to have a really full-fledged, meaningful conversation to process natural language in a really meaningful way, we're still, there's still a lot of progress that needs to be made. And so I think, those are some of the exciting areas. And of course, some of the things I've talked about, I think there's still a lot to be done in multi-agent systems and robotics, in machine learning in general. With regards to whether we can beat the World Cup champions by the year 2050, one of the reasons that people picked the year 2050 was that it's a time when it's likely to be, all the people who started working on it are likely to be retired by then. So you won't hold it against us if it doesn't happen. But that amount of time we have left is still pretty long when you think about it. I mean, from the examples I often give are from the Wright brothers' first airplane flight to landing a man on the moon was less than 70 years. From Watson and Crick discovering the double helix model of DNA to sequencing the entire human genome was on the order of about 50 years. From the first computer that could do anything at all, the first digital computer, to beating the human chess champion was about 50 years. And so all of those things seemed completely unbelievable and out of reach, and yet were achieved. And I think beating the World Cup champions on a real soccer field today seems completely out of reach and unbelievable. But like I say, I've been surprised before. We're making great progress. We're certainly a lot closer than we were 20 years ago. And so I wouldn't bet too much on it, but I also wouldn't bet against it.
All right. Yeah. Thank you for your time and for such a great talk. It's an honor to have you.
Thanks for inviting me, and thanks everybody for being here.
All right. Good night, everyone. And again, thank you for attending. Bye.
So long.